Welcome all. Today we'll learn about the Hall effect experiment here. Now this Hall effect setup, you can see it here. This is the Hall effect setup. Now let us understand what is Hall effect first. Now Hall effect experiment is basically done to identify the density of charges and also to identify Hall coefficient. So first let us understand what is Hall effect. Now Hall effect is a phenomena in which, like, when you have a conductor or a semiconductor carrying some current is placed in a transverse magnetic field, then transfers to both magnetic field and current, we have an Hall voltage generated. And this was actually first given by Edwin Hall, so it is named after him as a Hall voltage. So this potential difference is measured here as a Hall voltage. So I have the setup here for the same. Now here we have a Gauss meter. Now we have a constant power supply and we have an electromagnetic power supply here and we have magnets here. So this is an electromagnetic field where we have connected electric field to the magnetic field here. So this is the whole setup about the Hall effect. Now experimentally we'll see how we have to measure the Hall coefficient and also how to identify density of charges. So here is a Gauss meter. Now this Gauss meter is used to measure the magnetic field. Now here we have a Gauss probe. Now this is called as a Gauss probe. When a Gauss probe is placed between the magnets, we can identify what is the magnetic field. Now let us see how much is the magnetic field between the magnets placed here. But before that, let us give some current here, that is constant current, to make this as an electromagnetic field. So you can see the connection. The connection is quite simple. You just have to connect from the magnet to the electric field. Now let us give some constant current here, about 0.3 or 0.4. Now this is 0.4 amperes of current what I am giving here. And now let us measure the magnetic field here. So place the Gauss probe between the magnets here and you can find the value on the meter, Gauss meter there. So this is the amount of magnetic field which is present between the magnets. Now once you measure it, we don't need this as of now, we'll switch it off. Now you can see this is a sample given to you, like this is a semiconductor sample actually. The silver colored piece what you're seeing, this is a semiconductor crystal here. Okay, now we can see there are 4 probes connected to the sample. Now here these 2 probes are connected to the sample to measure, the current here. Obviously you can see that when these 2 are the current, obviously perpendicular to current we have the magnetic field, and these 2 probes what you're seeing here are connected to the voltmeter to measure how much is the voltage produced here. So this voltage we call it as a Hall voltage. Now let us see how to measure this. Now just make the connection, the simple connections here. Is a Hall probe, and we'll place the Hall probe slowly into the magnetic field. Right. Once you place it in the magnetic field, now here is a simple connection. We connected it to the voltmeter and ammeter. So here is my voltmeter. This is an ammeter here. Now as of now you can see the current is 0 and voltage is also 0. Okay. Now as you increase the current, you can see there is a change in the voltage slowly happening, and at the same time you can also identify that there is a negative sign here. The negative sign on the Hall voltage indicates that the sample given to you is a negative type sample, that is N-type sample. Okay. Now corresponding to the changes of the current, you have to find the voltage. So now as you increase the current, you can observe that there is a change in the voltage, right? At the same time, you can also observe that there is a negative sign here. Now the negative sign for the Hall voltage indicates that the sample given to us is an N-type sample. Okay. Now if this value is positive, then the sample given to us is P-type. So this is how you can identify that what type of a sample is given to you if the sample is unknown to us. Now here as you increase the current, you will see that there is a change in the voltage. Tabulate all the values of corresponding changes of current to the voltage. Now once you finish this, bring it back to 0. Now increase this electromagnetic field to a little higher value than what we have done earlier, and we'll observe that the small changes again happens in the same way as the current increases. You'll see the voltage also increasing. So tabulate this values also now. Now once you finish this, switch it off. Then take the Gauss probe again, measure the magnetic field there. Now let us see how to tabulate the values and see how to calculate the value. Now the thickness of the sample is given on the sample itself, so it is around 0.67 mm. Now we have noted the magnetic fields also and the constant current at which we are doing the experiment. Of course, these values are different. I'm just showing you an example. Now once you tabulate the values of current versus voltage, now this is how we have to do it for two different values of the constant currents, right? Now once you have this, the formula to calculate your Hall coefficient is RH. The Hall coefficient RH is calculated as VH by IH, that is Hall voltage by Hall current into the thickness of the sample by the magnetic field for that constant. Now how do you find this VH by IH value? This is actually the slope of the graph. Now you need to plot a graph between Hall and voltage, and we have got two different constants, so we have different graphs. So I did the slope of the graphs. Now for example, if this is the first case of the constant current IH1 and say this is for IH2, then the slope of this is substituted here, that is VH by IH is the slope that is substituted here, and the T is the thickness of the sample is already given as 0.67 mm for this particular case of your sample by the magnetic field what you have noted in the gauss meter. So this will give you RH value. And how do you identify the density of charges? Density of charges is given by N. N is equal to 1 by RH into the charge of the electrons. Okay. Now actually if you see here, N value is calculated from RH. So first we need to calculate the RH value into the charge of the electrons. So this is how it is actually calculated. Once it is calculated, you have both the values now, RH value and also N value. This is the density of the charges, that is number of charges available.